Good morning, all of you. In this session, I am going to explain about simple problems on bolted joints. First of all, you have to know the fundamentals about stresses. Stresses induced in screwed fasteners due to static loading. The following stresses in screwed fastening due to static loading are important from the subject point of view. First one is internal stresses due to screwing up forces. And second one is stresses due to external forces. And last one is stresses due to combination of stresses. Okay, at 1 and 2. Okay, that is the internal stresses due to screwing up forces and stresses due to external forces. Okay, combined stresses, that means. Now we shall discuss these three forces, these three stresses in detail. Initial stresses due to screwing up forces. Okay, the following stresses are induced in bolt, screw, or stud when it is screwed up tightly. Tensile stresses due to stretching of bolt. First one is tensile stresses due to stretching of bolt. Okay, okay, this is a bolt. When you are applying two equal and opposite pulling forces. Okay, when you are applying two equal and opposite pulling forces, then tensile tensile stresses will induce in these bolt material. Okay, so Pi is the initial tension in the bolt due to tensile loads. Okay, so this is one Pi. Pi is the initial tension in the bolt. Okay, Pi equal to 2840 into D is the formula for initial tension in the bolt. Okay, here small d is the diameter, nominal diameter of the bolt. Okay, n is the newtons. Okay, SI units for load, newtons. Now in similar way, Pi equal to 1420 into D. Okay, here D also nominal diameter of the bolt, n is the units for load. Okay, now this formula is used for steam engine cylinder cover joints. Okay, fluid tight. Okay, this formula is used for design of fluid tight like steam engine cylinder cover joints. Okay, and this formula is used for light. Okay, this formula is not used. Sorry, this formula is used when there is no need of a tight joint. Okay, fluid tight joint. Okay, torsional shear stress caused by the frictional resistance of the threads during its tightening. Okay, when you are applying a compression force, okay, that means when you are applying a compressive forces on bolt or nut, then you have to use this torsional equation. Already we know the formula for torsional equation, that is tau by r equal to t by j equal to c into theta by l. That is the torsional equation. From the torsional equation, you have to determine the shear stresses induced in the bolt material. Tau is the shear stress induced in the bolt material. R is the radius of a radius of a bolt, and T is the torque induced in the bolt material, and J is the polar moment of inertia for bolt. Okay, now this is the formula for shear stress induced in the bolt. Tau equal to 16T by pi d cube. D is the core diameter of the bolt. Core diameter. Okay, core diameter or a nominal diameter. Okay, and third one is shear stresses across the threads. The average thread shearing stresses for the screw is obtained by using this relation tau s equal to P by pi dc into B into N. Here N is the number of bolts required, and B is the width of the thread section at the root. Okay, and DC is the core diameter of the bolt, and P is the load. Okay, now shearing load. P is the shearing load. Okay, tau S is the shear stress across the threads. Okay, now this is the formula for average shear stress. Okay, for nut. For nut, average shear stress for nut tau n equal to P by pi d into B into N. Here D is the major diameter or outer diameter of the bolt. Okay, here DC is the core diameter. Okay, core diameter of the bolt. D is the major diameter or outer diameter of the bolt. Okay, bolt. Now compression or crushing stresses on threads. The compression or crushing stresses between the threads sigma c may be obtained by using this relation sigma c equal to P by pi into D square minus DC square into N. N is the number of threads in engagement. Okay, N is the number of threads in engagement, and D is the outer diameter of the bolt, and DC is the core diameter of the bolt. Okay, outer diameter also known as major diameter. Okay, DC core diameter also known as minor diameter. Okay, P is the load acting on the bolt or nut. Bending stress, if the surfaces under the head or nut are not perfectly parallel to the bolt axis, then you have to use this formula, that is a bending stress induced in the bolt material, sigma b equal to x into E by 2L. Here x is the difference in height between the extreme corners of the nut or head. Okay, here capital E is the Young's modulus or modulus of elasticity for bolt material. Okay, L is the length of the shank of the bolt, that is the length of the bolt. Okay, L is the length of the bolt or length of the shank bolt. Okay, now the stresses induced in the bolt material due to external forces acting on the bolt. First one is the tensile stresses. Okay, the bolts, studs, and nuts usually carry a load in the direction of the bolt axis, which induces a tensile stress in the bolt. Okay, DC is the root or core diameter of the thread or minor diameter of the thread. Minor diameter DC. Sigma T is the permissible tensile stress for bolt material. Okay. Now this is the formula for load. Tensile load. Already we know that stress equal to load by cross section area. Okay, already we know the formula for stress equal to load by area. Okay, so from that equation, load equal to stress into area. Okay, here the cross sectional area of a bolt is pi by 4 d square. Here DC is the core diameter. Okay, you have to consider solid area. Okay, so you have to consider core diameter or minor diameter of the bolt. Okay, so this is the cross sectional area. Pi by 4 DC square is the cross sectional area of the bolt. Okay, sigma T is the stress induced in the tensile stress induced in the bolt material. Okay, from this relation you have to determine the value of core diameter DC. DC equal to square root of 4p divided by pi into sigma T. Okay, now if the external load is taken up by a number of bolts, then you have to use this formula. Okay, so number of bolts, if the number of bolts are given, then you have to use this formula for determining the load acting on the bolt. Okay, now shear stress induced in the bolt material. Sometimes the bolts are used to prevent the relative movement of two or more parts, as in case of flange coupling. Then the shear stress is induced in the bolts. The shear stresses should be avoided as far as possible. It should be noted that when the bolts are subject to direct shearing loads, they should be located in such a way that the shearing load comes up upon the the body of the bolt, and not upon the threaded portion. Okay, here small d is the major diameter or outer diameter of the bolt. N is the number of bolts. Okay, already we know the formula for shear stress. Shear stress equal to shear load by resisting area. Shear load, PS is the shear load, and resisting area is pi by 4 d square. Here d is the outer diameter of the bolt. Okay, this is the resisting area of the bolt. That is also cross section area pi by 4 d square. But in this condition, you have to consider outer diameter. Okay, now tau is the shear stress, n is the number of bolts. From this equation, you can get the value of diameter, outer diameter of the bolt, d equal to square root of 4 ps by pi into tau into n. Okay, now this is the formula for combined tensile and shear stresses. Okay, when 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 you are applying tensile and compressive forces, tensile or compressive forces and shear stresses on the bolt, then you have to use principal shear stress and maximum principal stress formulas. Okay, tau max is the maximum shear stress theory. Tau max equal to, from maximum principal stress theory, from maximum shear stress theory, you have to use these two formulas to determine the suitable diameter of the bolt. Okay, so tau max equal to 1 by 2 into square root of sigma t square plus 4 tau square. Here this one is tensile stress, tau is the shear stress, tau max is the maximum shear stress. Okay, now sigma t max is the maximum principal stress. Okay, so this table shows the standard dimensions of screw threads. This is the designation of threads: M04, M06, M08, M1, M1.2. M means metric thread. Okay, now M0.4 having pitch 0.1 mm and major or outer diameter 0.4. Okay, M0.4, M indicates outer diameter. So outer diameter equal to outer diameter or major diameter or nominal diameter equal to 0.4, and the effective or pitch diameter is 0.335. Okay, this one is the core diameter of the bolt. This one is the core diameter of the nut. Okay, now this is the depth of the thread, and this one is the stress area. Okay, so now these are also same for different sizes. Okay, these are also same, M7 to M60. These are the values for fine series. Okay, M8 indicates outer diameter of the thread, and one indicates the pitch of the threads. Okay, from these tables you have to select standard sizes. Okay, for design of bolts and nuts. Now this is the example problem number 1. Determine the safe tensile load for a bolt of M30, assuming a safe tensile stress of 42 megapascal. Okay, this is a given question. From this question, you have to determine the safe load acting on the bolt. Okay. So here from the given question you can observe the bolt size is M30. M30 means outer diameter of the bolt is 30 mm. Outer diameter or nominal diameter or major diameter. Major diameter M equal to 30 mm. Okay. Here the safe tensile stress acting on the bolt is 42 megapascal. That is tensile stress. Okay, tensile stress equal to 42 megapascal. 1 megapascal equal to 1 Newton per mm square. Okay. So these are the given values. Outer diameter of the bolt D equal to 30 mm and tensile stress sigma T equal to 42 megapascal. That is 42 Newton per mm square. Okay. Now you have to determine the value of load, safe load acting on the bolt. Okay. Already we know that formula load stress equal to load by cross section area. Okay. From mechanics of solid subject, already we learned stress equal to load by cross sectional area. So from this formula, load P equal to stress into area. This is the formula for load. Okay. So from this equation, you have to determine the value of load. Okay, safe load acting on the bolt. Okay. Here for determining the safe load, you have to identify the value of cross section area from standard table. Okay. So sigma T, here the tensile stress value is given, that is sigma T. Sigma T equal to 42 megapascal. Okay, here sigma equal to 42 megapascal. Now you have to select the cross section area for M30 bolt. Okay. For identifying the cross section area, you have to use a standard table. From standard table for M30 thread. Okay, so this is the designation of thread M30. For M30 nut, you have 3.5 mm pitch and 30 mm outer diameter. Okay, outer diameter is 30, D equal 30, and effective pitch diameter is 27.727 mm, and the core diameter of bolt is 25.706, and the core diameter of nut is 26.211 mm, and depth of thread is 2.147 mm, and the stress area is 561 mm square. Okay, so you have to select this value as area, stress area, capital A. Okay, now you have to substitute this value 561 in this equation. Then after you will get the value of load P. So here safe load equal to stress into area. Stress equal to 42 megapascal and the area, stress area equal to 561 from this table. For M30, M30 diameter thread, we have 561 mm square of stress area. Okay. So final answer is 23.562 kilonewtons. Okay. Now coming to the another example, problem number 2. Two machine parts are fastened together tightly by means of a 24 mm tap bolt. If the load tending to separate these parts is neglected, find the stress that is set up in the bolt by the initial tightening. Okay, this is a given question. From the question you have to identify the given values. First of all, the size of the bolt is 24 mm, that is the outer diameter of the bolt equal 24 mm. Okay, this is a tap bolt. Okay, and from standard table, first of all you have to select a core diameter of the bolt. Okay, for M24 bolt, the core diameter of the bolt is 20 point. Here for M24 size, the core diameter DC is the core diameter, DC equal to 20.320 for bolt. Okay, For nut 20.752. Okay, for nut. Okay, so you have to select the value of core diameter of the bolt. DC equal to 20.32 mm for M24 bolt. Okay, M24 bolt. So from this table, DC equal to 20.32 mm. That is the core diameter. Okay. From this table, the standard core size of bolt is 20.32. After getting the core diameter DC equal 20.32, you have to use standard formula, that is stress. Okay, here stress sigma T equal to stress setup in the bolt. Okay, so here the initial tension in the bolt is PI equal to 2840 into D for tight fluid tight joint for used for boilers. Okay, here D is the outer diameter of the bolt. Okay, that is a 24 mm. M24 is given, that is 24 mm is the outer diameter. Okay, D is the outer diameter, DC is the core diameter. Okay, so the initial tension in the bolt is bolt metal is 68,160 newtons. After that, you have to use stress formula. Okay, sigma stress equal to load by area, cross section area. For cross section area, you have to use core diameter. Okay, for cross section area, you have to use core diameter. Pi by 4 DC square is the cross section area. Sigma T is the stress. So for determine the value of P, you have to use sigma into A formula. Okay. Now substitute the value of P in this equation and sigma value. You can get here the value of cross section area equal pi by 4 DC square. Okay. Now you have to check the stress induced in the bolt material. Here the given stress is the obtained stress is 210 megapascal, that is 210 Newton per mm square. This is the stress induced in the bolt material. Now coming to the another example problem, this is a I bolt. Okay, an I bolt is to be used for lifting a load of 60 kilonewtons. Find the nominal diameter of the bolt if the tensile stress is not to exceed 100 megapascal. Assume core threads. Okay, here from the given question, the load acting on the I bolt is 60 kilonewtons. That is P equals 60 kilonewtons. That means 60,000 newtons is the load acting on the bolt, and here the stress, tensile stress sigma T equal to 100 megapascal. Okay, now you have to determine the nominal diameter small d. That is also outer diameter of the thread. Okay, outer diameter of the thread small d. Load acting on the I bolt P equals 60,000 newtons. 10 power 3. Okay, 60,000 newtons. And the tensile stress equal to 100 megapascal. Here from this figure, small d equal to outer diameter of the thread and DC is the core diameter of the thread. Already we know that the load acting on the bolt P equal to from the equation stress equal to load by area, load by cross section area. Okay, load by cross section area. From this equation, the load P equal to load acting on the bolt P equal to stress into cross section area. From this equation, you have to determine the value of diameter, core diameter DC. Okay, here the load P equal to is 60,000 newtons. and the value sigma equal to 100 Newton per mm square. Capital A is the cross section area of the bolt, power 4 DC square. Cross section area is the power 4 DC square. For cross section areas, you have to consider core diameter. Okay, power 4 DC square. From this equation, the core diameter of the bolt DC equal to 27.6 mm. Okay, this is the core diameter or minor diameter. Okay, after getting the core diameter DC, you have to determine the value of outer diameter small d. Okay, that is the nominal diameter. Okay, so from the standard table, you have to select the value of standard size. For core diameter 27.6, here you can observe. Okay, from this table, the nearest value is 28.706 is the nearest value. So for this diameter, for this core diameters, the standard outer diameter of the bolt is 33 mm. Okay, nominal diameter or outer diameter or major diameter is M33. That means 33 mm is the outer diameter of the bolt. Okay, this is the answer for this problem. Okay, now coming to another example. Two shafts are connected by means of a flange coupling to transmit torque of 25 Newton meter. The flanges of the coupling are fastened by 4 bolts of the same material at a radius of 30 mm. Find the size of the bolts if the allowable shear stress for the bolt material is 30 megapascal. Okay, here the application of a bolt is flange coupling. Okay, for join the flanges, we are using bolts. This is the example diagram. Okay, yeah, these are the bolts. Okay, these bolts are used to join these two flanges. Okay, so from the given question, first of all, you have to identify the given values. Okay, here in question, torque is given, torque T equal 25 Newton meter. Okay, 1 meter equal to 1000 mm. So 25 into 1000 Newton mm is the torque. Okay, torque equal to force into distance. Okay, so 25 Newton meter is the torque, and here the number of bolts used for join the flange coupling is N equal to 4 bolts, and the shear stress induced in the bolt material is 30 megapascal. Okay, shear stress induced in the bolt material is 30 megapascal, and the radius of the pitch circle of the bolt. Pitch circle of the bolt is given, that is RP equal to 30 mm is the radius of a pitch circle. Okay, radius of a circle. Already we know that shearing load carried by the flange coupling equal to PS equal to torque by radius. Okay, PS is the shearing load. Shearing load equal to torque by radius of a flange. Okay, so radius of a pitch circle RP. Here the value of RP equal to 30 mm and torque T equal to 25,000 Newton mm. Okay, now substitute the value of T and RP in this equation. You can get the value of PS, that is the shear load. Shear load acting on the bolts. Okay, 833.3 newtons is the shear load acting on the bolts. After getting the shear load, you have to determine the value of here. Yeah, after getting the value of shear load, you have to determine the suitable size of the bolt. Okay, let DC is the core diameter of the bolt, core diameter or minor diameter of the bolt. Okay, already we know the formula for shear stress. Okay, so here tau is the shear stress. Shear stress equal to shear load. Shear load divided by shearing area. Shear load divided by shearing area. Okay, so for shear area, for shearing area, you have to consider outer diameter. So pi by 4 d square into tau. Pi by 4 d square is the area and tau is the shear stress, n is the number of bolts. From this equation, ps equal to shear load, ps equal to shear stress into area. Okay, for n number of bolts, you have to consider n. That means load acting on each bolt. Okay, load acting on each bolt, shear load acting on each bolt equal to tau into area into n number of bolts. Okay, already we know the value of ps. Okay, already we found that value ps, so substitute that value. And also we know the value of tau, shear stress, and as is the area, pi by 4 d square is the cross section area, n is the number of bolts, n equal to 4. Okay, from given data, n equal to 4, tau equal to 30. Okay, so this is the value of shear load. From equation 1 and equation 2, you can get the value of core diameter of the bolt. Okay, dc equal to 2.97 mm is the required size of the bolt. Okay, required core diameter of the bolt. That means we need minimum 3 mm outer diameter of the bolt. Okay, minimum we need 3 mm size bolts. Okay, or